Hello, my name is Rohan-Paul and very welcome to my computer vision and deep learning YouTube channel. Let's get started. So in this video, I will do DCGAN or Deep Convolutional Generative Adversarial Network implementation from scratch. So I'm looking at the original paper that was published in 2016 by the researchers Alec Radford, Luke Meds, and Soumit Chintala. And here in DCGAN, like all other GANs, we have two neural networks. One is generator and the other one is discriminator. The generator's objective is to learn the data distribution for the training data to produce fake images that resemble the training data. And the discriminator is a classifier whose objective is to distinguish the real images from the fake data generated by the generator. Every time the discriminator detects the fake data generated by the generator, then the generator is penalized. So basically the generator and the discriminator are pitted against each other as the generator tries to fool the discriminator and the discriminator learns not to get fooled by the generator. Both the generator and the discriminator are neural networks, of course. Input to the generator is a random noise vector, what you see here at the very start of the network, which is a 100-dimensional vector represented by this letter Z. And so this is the input to the generator. Whole generator network starts with these input vector, which is a random noise vector. In contrast, the discriminator is the classifier here. That means the job of the discriminator is to classify the images generated by the generator. So the input to the discriminator is the output from the generator, which are fake data, and also the real images from the training data. The discriminator loss penalizes the discriminator for misclassifying real data as fake or fake data as real. This is the architecture of a DCGAN. So now first let's understand how traditional image processing works. So traditionally ConvNet uses a network that takes an image with the dimensions height, width, and number of color channels as input, and through a series of convolution layers outputs a single vector of class scores with the dimension of 1 into n, where n is a number of class labels. In DCGAN, however, under the generator part, to generate an image by using the ConvNet architecture, we reverse the process. Instead of taking an image and processing it into a vector, we take a vector and upsize it to an image. That's what this part is doing. So overall, the core of DCGAN architecture uses a standard CNN architecture on the discriminative part of the model, but for the generator, convolutions are replaced with up convolutions. So the representation at each layer of the generator is actually successively larger as it maps from a low dimensional latent vector onto a high dimensional image. It needs a layer to translate from coarse salient features to a more dense and detailed output. Now let's quickly go through the original paper that was published in Jan 2016 by Alec Radford and Luke Meds and Soumit Chintala. So the original paper mentioned few things to stabilize GAN. Like I discussed earlier, that GAN by itself is super sensitive to parameters, and DCGAN is even more so. So the architecture guideline that they have given for a stable DCGAN are the following: replace any pooling layers with strided convolutions or discriminator and fractional strided convolutions or generator. Use batch norm in both the generator and the discriminator. Remove fully connected hidden layers for deeper architectures. Use ReLU activation in generator for all layers except for the output, which uses tan-H. Use leaky ReLU activation in the discriminator for all layers. And one of the most important point in this architecture is that the generator part of the network uses a transposed convolution to convert a 100-dimensional vector to a fully fledged image by the end of this network here. In contrast, the discriminator part of the network uses these output from the generator, which is a fully fledged image, and converts it ultimately by the end of the network, that is end of the discriminator network, into a binary decision of 0 and 1, and this is done in the discriminator by use of a normal regular convolution. Now quickly see what is transposed convolution as opposed to a regular convolution. Alright, with that background on the architectural details, let's start the actual implementation. So I am back in my VS Code, and to implement the entire project I will have 3 files, which is what we can see right now in the screen. One is DCGAN, which will have the actual implementation of the generator and the discriminator methods and the classes actually. Then I will have a train file which will implement just the training the architecture, and I will also have a small utils.py file which will have couple of methods to get the data and pre-process the data, etc. So before starting the actual architecture, let's quickly see what the original paper talks about the guidelines on the architectural implementation. So remember, like many GANs, DCGAN is very unstable. So that means that because of its architecture, slight problems in the initial part of the training or in the structure of the training can make your entire architecture produce only noises. So we have to be very careful about that, and that's why the original paper clearly says architecture guidelines for stable deep convolutional GANs are the following, which are: replace any pooling layers with strided convolution in the discriminator and fractional strided convolution in the generator. Then use batch norm in both the generator and the discriminator. Remove fully connected hidden layers for deeper architectures. Use ReLU activation in generator for all layers except for the output, which uses tanh, and use leaky ReLU. Now remember, this last point is this they are talking about using leaky ReLU and not the ReLU for the discriminator for all layers. All right, now let's go back to the VS Code. Okay, so I'm in my DCGAN.py file. This will have the main implementation of the generator and the discriminator class. Initially, I'm just importing all the standard imports, and then my generator class is here. So the generator takes the noise vector as an input to generate the images that will resemble the training dataset. And here my training dataset is MNIST, that is they're all grayscale, and the shapes are 1 by 28 by 28, that is number of channels are 1, height and width both are 28. So the entire generator class will convert the noise vector to 1 by 28 by 28 images which resemble MNIST dataset, and it accomplishes this through a series of strided two-dimensional transposed convolution. So I'll be using this method of PyTorch nn.conv transpose 2D. These layers are paired with batch norm 2D layers, as they help with the flow of gradients during training, which is followed by a ReLU activation function. So let's see. So this is my generator class, and the arguments to the class is mainly these number of channels, noise vector, and number of generator filter, that is num gen filter, these variable. This represents the total number of generator filters or number of channels in the generator. So my first, it starts with these nn.conv2d within a nn.sequential module. So the first conv2d layer takes in channels as a noise vector, which is coming from the argument. This will be a 100 dimensional, that is 100 element vector, and the out channels that represent the number of output channels, or the number of filters, which will be in this case these num gen filter into 4. Now remember, these out channels or the number of filters is a hyperparameter, so it is you are supposed to tune it to get best results. So you could actually change it according to your dataset, according to your architecture, etc. So I have taken here this particular number, num gen filter into 4. Kernel size I'm taking 4, stride 1, padding 0, and bias I'm taking false. That's because in the next line I'm using nn.batchnorm2d. Now, why does batch norm needs to set bias equal to false in PyTorch is because batch normalization already includes the addition of the bias term. So the point to note here is that batch norm learns the mean and standard deviation of the y vector over many batches and uses that to recenter and rescale the data, that is standardization of the data, and including bias in previous layer will be cancelled here. And that's why you will see that in this architecture as well, I'm including bias equal to false here and here as well and here as well. I mean, in the all the conf transpose 2D layers where I have a batch norm after immediately after it. So overall, in my generator class, the height and width dimension of the input image does not change, only the channel dimension decreases. We can see that. So we have one conf transpose 2D, then the second one, third one, and fourth one. So total 4 conf transpose 2D. And each of these conf transpose 2D is followed by a batch norm ReLU, then batch norm ReLU here again, then the batch norm and ReLU. And because this is the final conf transpose 2D, I do not have a batch norm 2D after it, and instead of the ReLU I have tan-H. This is exactly following the architectural guidelines that was mentioned here in the original paper. All right, and we can see these output channels continues to decrease because the first one out channels is numgen filter into 4. Then for the next one I have out channel is numgen filter into 2. For the third one, out channel is only no multiplication, it's a purely numgen filter, and later we will see this number, this out channel, I will give it the number 32 for both my discriminator and the generator as well. And finally, in the final conf transpose 2D as well, the out channel remains the number of channels here, because this is a final one and it has to produce a final image set which should resemble the MNIST dataset, and we know the MNIST dataset, the channel number is 1 because they are all grayscale. So that was the sequential stacking of my 4 conf transpose 2D, and then I have to do the forward function. This is just quite easy here. So forward is just the output from the network, and I'm returning that output. And obviously this network, that is the self.network, is the name of this entire architecture. So I'm naming it all the nn.sequential individual stacking to be self.network here, and that's exactly what I'm using within my forward function. Okay, now next is discriminator. And for the discriminator, quickly have a look at the architecture again. So the generator ends here outputting is images that are fake images and that resemble, in my case, the MNIST dataset. So here in this picture we are seeing 3 channels because I'm looking at the original image given in the original paper, which implements the entire architecture on celeb A dataset, which are color images, and they have 3 channels. But in my case, MNIST dataset, it will have 1 channel only. So anyway, the point is generator will produce this final image as its output, and discriminator starts from that image. So input to the discriminator is the output from the generator. That is, I am feeding the discriminator this fake image generated by the generator, and now discriminator will classify them as either fake or real. Fake will produce 0 and real will produce 1. So here my discriminator starts. So the main difference is that generator will use conv2D, that is transposed convolution, to increase from vector to image and to continuously apply it to reduce the number of channels and ultimately produce the image. And the discriminator is the opposite. It will use a normal convolution and will increase the depth or the number of channels continuously through various application of those convolution layers. So here is my discriminator class in the same file, DCGAN.py. So again, the discriminator is a binary classification neural network to classify the input as real or fake images of dimension 1 by 28 by 28. In this case, the inputs to the discriminator are real images from the training dataset and also the fake images generated by the generator. The discriminator outputs a scalar probability to classify the input images as real or fake. So it's a binary classification problem. Now look at the architecture the way that I'm implementing. So here instead of this conv transpose 2D, each layer will have conv 2D. This is a normal convolution. So I will have 4 of them, 1, 2, 3, 4. And the original paper clearly talks about that use leaky ReLU activation in the discriminator for all layers, and use strided convolution for discriminator. And anything else? Batch norm. Yeah, obviously you have to use batch norm in both the generator and the discriminator. All right, now going back to my code. Okay, so again, discriminator starts from the in channels to the first layer will be the number of channels, because that's the final output from my generator. Remember, the out channel in the final layer of my generator function, that is the fourth output from the fourth conf transpose 2D. The out channel was num channel. This is MNIST dataset, so number of channel will be 1, and that will be the starting in channels for my discriminator. Here I am in the discriminator class. In channels is num channel, num underscore ch. This will be 1. Out channel will be the number of discriminator filter. Here again, this is coming from the arguments, and later we will see in my train.py file, while I will actually start the training, that I am giving this variable a number of 32. That is, this will be my number of filters or number of channels in my discriminator. Kernel size keeping at 4, stride 2, padding 1, bias false again for the same reason, and that we discussed earlier. And here I'm then using leaky ReLU for it, and then the next conf2d here, and here in channels is again num discriminator filter, that because that's output channel from the previous layer. And out channel remains out channel. I have to here increase the depth, and that's what exactly we saw in the image, that in generator. Let's quickly have a look at the image again. That is, in the generator, the depth, that is the number of channels, are reducing. So here we can see 1024512256 that again I'm looking at the original paper image, the image given in the original paper. So this number of channels will not exactly match with my implementation, because I'm doing it on MNIST dataset and they did it on Celeb A dataset. So anyway, the point here is that in the generator, the number of channels will continue to decrease layer by layer, and the opposite will happen in the discriminator. Here the number of channels will continue to increase layer by layer, and that's what we will be seeing in the code. So in the next conf2d, that is a second conf2d within my discriminator class, the out channel I'm increasing by a factor of 2, and then I have the batch norm 2d, leaky ReLU. Now a quick word on use of leaky ReLU here. We already know that DCGAN, by its definition, it's very unstable, so you have to be very careful on the implementation of these layers and use of various hyperparameter. And leaky ReLU, it has been found, helps in faster convergence if your output requires both positive and negative values. But the catch is that you need to tune the negative slope of leaky ReLU, which is a hyperparameter, to get a better accuracy, and the negative slope is this number 0.2. So negative slope in this context means that the negative half of the leaky ReLU slope. It is not describing a slope which is necessarily negative. So yeah, that's about the leaky ReLU. So yeah, so after my conf2d, second conf2d, again I'm going to the third conf2d, and here again I'm increasing the in channels to be num descriptor filter into 4. Okay, see, this is coming from the previous channel, because that was done, the increase of the number of channels was done in the third conf2d, and that's exactly I have to take in my fourth and final conf2d. And out channels here remains 1, obviously, because this is MNIST dataset, grayscale 1 channel. Kernel size keeping at 4, stride 1, padding 0, bias false, and finally I will be applying nn.sigmoid function for the final layer. Now for the forward function, quickly remember this point, it's very important. I should mention it in a comment that the discriminator outputs a scalar probability to classify the input image as real or fake. So ultimately discriminator will give me a 0 or 1 based on if it is real, if it is fake or real. If fake equal to 0, real equal to 1. Now the forward pass in the discriminator is that's what is happening here. The input is an image tensor and returns a one-dimensional tensor representing image as fake or real. That's why I'm using dot view here, which will kind of flatten the tensor, and also I'm using squeeze one, which will remove all superficial one dimension from the tensor. And with that, I'm done with the implementation of the generator and DCGAN architecture actually. And I can now go to my, I can actually start the training, but obviously before starting the training, quickly have a look at the utils file here, because here I will have two small methods just to help in the training. So the first one is obvious, that you will see in all PyTorch image dataset project. That is, you have to get your data loader method running. So here I'm just making use of the Torch Vision MNIST dataset. Obviously at the very start I'm importing all the Torch Vision.utils function, datasets and transforms. And then for the transform, I'm only applying the two tensor method, and also I'm normalizing the data with this mean of 0.1307 and standard deviation of 0.3081. And why I took this number is because in many projects that I found in various sources, this kind of the two numbers that was used mostly on MNIST dataset to normalize it. And then my trained dataset variable will just be the downloaded dataset from datasets.mnist. This is coming from Torch Vision. I just mentioned my root folder to be my Google Drive. Train true transform is applying this transform that I am previously defined, download equal to true. That means if it is already there, that is the data is already there, it will not download it again, otherwise it will download it. And then I'm making use of torch.utils.data loader to load these trained data set so that it will fetch the entire batch by batch data from the entire data set and feed it to the model. And finally, from these get data loader function, I'm just returning the train loader. This is just each batch of data that it will be fed into the model. And another method, quick small method, I'm using this plot images. This is just a simple method just for plotting, no calculations, no complex here at all. It is just making use of plt.subplots so that when my epochs are done, I can see what kind of results ultimately it produces. That is, what kind of images is produced from the generator class of my DCGAN, because visually I can see at least the result. So basically, it is just creating a grid of the grid will represent the overall plot, and then it will take a number of samples from my output images to be plotted, and then it is just making use of these plt.subplot to plot it from that sample. And yeah, so that's my plot function. And now coming back to train.py. So this is where I will implement the entire training of my DCGAN architecture. So let's before starting on that, let's quickly go over some guidelines for training DCGAN. So this is that slide, the training steps for the generator. So these are the steps that I'm going to implement in my generator and discriminator within my train.py file. So under the discriminator, so by convention, normally many people starts with the discriminator within the training class, and that's what I will do as well. So it will start with the input. The discriminator will get it input as the real data from training dataset and also the fake data from the generator. Then the discriminator classifies between real and fake data. Every time the discriminator misclassifies a real instance as fake or a fake instance as real, it penalizes the discriminator. That is, a loss will increase. And then it back propagate through the discriminator and update the discriminator's weight based on its loss. So let's implement that, and then before implementing the generator, we'll look into these other guidelines. That is, the discriminator updates its weight through back propagations from the discriminator loss through the discriminator network. Another super important point when training DCGAN, that is keep the generator constant during the discriminator training phase, because when training the generator, we do not want the discriminator to change, else we will be expecting the generator learn a moving target, and as a result the generator will never converge. And also just exactly keep the discriminator constant during the generator training phase. That's because when training the discriminator, we do not want the generator to change, as we want the discriminator to learn how to classify the real data from fake data. And now I'm back in my VS Code. First, the initial imports are all the usual ones. I'm also defining the device to use GPU if available, else CPU. And here in these two lines, I'm importing all the classes from my other two files, that is DCGAN.py and utils.py. And here is a main method in this file, that is train method. And the train method takes all these arguments, number of epochs, discriminator net, which will be the generated object from this generator, from the discriminator class, and similarly discriminator net and generator net, which will be coming from the classes from this file. And optimizer for discriminator, optimizer D, optimizer for generator for the generator class. Train loader, which will be my batch by batch data set, which will be coming from invoking this function that I defined in utils.py, that is get data loader. Train loader is what this method returns, and that's what I will be using as a training data. Then I have two variables that will be defined inside, that is fake label and real label. Actually, they will be passed as an argument. Sorry, I will define it outside of the function later, down here, when I'll just before executing this train method. All right, criterion, that's my loss function. And also a couple of other, this output path is just a path variable that where I will be saving the images that will be created by the generator network. That is, this will be the path where the fake images will be saved. Number of test sample is just some random number on which I will be applying the this is just a number of test samples which I will be plotting by using this method here, that is plot images. And yeah, device is just device what I already have defined here, that is my GPU or CPU, depending on whatever is available. All right, with that, now inside the function, number of batches obviously will be the length of train loader, because this train loader will give me batch by batch data. So that will be the length of this train loader. And then inside the function, I'll just am running the loop for each number of epochs. So in this case, I think I ran after running for 50 or 60 epochs, I got really reasonably good results. That is, my fake images were almost looking like the real ones. So this is just number of epochs, and then the real juice starts here. So I'm looping over or enumerating over my train data. First, I'm getting the batch size by taking the shape, the 0th element of this shape. And then from here, the discriminator network training starts. First, I'm applying 0 grad. And why I'm using this 0 grad at the very start of the training, that's because in PyTorch, for every mini batch during the training phase, we typically want to explicitly set the gradients to 0 before starting to do back propagation. That is, before updating the weights and biases, because PyTorch accumulates the gradients on subsequent backward passes. And because of this accumulation behavior in PyTorch, when you start your training loop, ideally you should zero out the gradients so that you do the parameter update correctly. Otherwise, the gradients would be a combination of the old gradients, that is, old which you have already used to update your model parameters, and also the newly computed gradient. It would therefore point in some other direction than the intended direction towards minimum or maximum. Hence, this is a standard behavior, a standard implementation of code that you will see in almost all PyTorch projects. All right, now my real images, I'm transferring them to device, and that's coming from, these real images are my actual training images coming from enumerating over the train loader data set. And now I have to create label. And first I'm training the discriminator on real images, and hence these my initial label creation will be filled with all one, and that's what I'm doing here. Torch.full batch size real images, real labels, device equal to device. So here these variable batch size real images, it's just a number of samples in a batch, so that many labels would need to be created. And real label, this is coming from the argument here, and later we will see that this will be number 1 because it is a 0-1 binary problem in discriminator. So my fake labels will be 0, real labels will be 1. All right, then the discriminator, so before this line, output equal to discriminator net real images. So basically here I am for the first time classifying my real images with the discriminator network. So that's the job of the discriminator network, that is, it is used to classify real images drawn from the training set and also fake images produced by the discriminator. So that's exactly how I'm doing in this line, that is classifying. The next 2 lines, actually I don't need them, I have commented out anyway, but I can actually delete them. This was because I was getting some float 32 problem while implementing this, and so I had to explicitly set both the output and labels to torch.float32, but later I resolved it by initiating the variables to be of float type. So let's just delete them. All right, now that my output is ready, that is, my classification is done with the discriminator network, I am ready to do my loss calculation. And for loss, I'll be using this criterion. Later we will see this criterion. I will be defining it to be binary cross entropy loss because it's a binary problem. So I'll be using PyTorch's BCE loss, and to that I will pass the result from these discriminator net, that is output variable, and also the ground truth, that is label that I have created earlier. And then I will apply my backward function to start the backward propagation. And here I'm just creating these extra variable d underscore x. This is just pretty much for logging purpose. That is, well, I will be running all the epochs. After each epoch I want to output and see what kind of output I am getting after each epoch, and that's why I have created this extra variable and taking the mean of all these outputs and also extracting the actual value from these by using the item method. So anyway, this line does not explicitly affect the overall training. It is just for my output logging purpose. And next, very importantly, I have to create this noise by using the torch.random. So I'm pretty much here creating a random noise vector or variable for the input to the whole adversarial network. And yeah, so batch, again, the size of the noise vector, it will be the number of batch size, which I have these batch size is just a number of samples in each batch. And noise vector, I will define it. This is part of the argument. Noise vector, where is the noise vector? Yeah, I see that I missed inputting that in my arguments list. So noise vector will just be another argument to my train function. Noise vector equal to, noise vector is just another argument, and later while executing the train method I have to pass this argument, and we will see that this noise vector, as per the paper, it's a 100-dimensional single vector. So that's what we will do later. Anyway, so this is that noise vector, which is the input for the entire adversarial network. And then the fake images, that's output from my generator class, that is this class. Remember, we talked about in detail this generator class. Entire output would be generated from a noise vector, and ultimately after all these convolution it will output an image which is of shape 1 by 28 by 28, resembling MNIST dataset. So that's what I'm doing in this line. Fake images generated by the generator class is generator net, and to that I'm passing this noise. And obviously generator net is part of the arguments, and we will see that this is an object of the generator class that we will define immediately after defining this train function. And now that I have created fake images, my discriminator network also needs to be trained on the fake images, and so I have to create some labels which are for the fake images. So now training on fake images, fill labels with 0. So that's what I'm doing. The same label variable here, I'll be filling them with fake label. This is an argument, and this will be given a number of 0 because they represent the fake. So now again, train the discriminator, that is classify these fake images with the discriminator net. And that's what I'm doing here in this line. Output equal to discriminator net fake images dot detach. Detach is just to detach my gradients from the tensor, because PyTorch's tensors automatically by default will have the gradients included it. So by detach method will detach the unnecessary gradient layer from the tensor. And now after this output, I am ready to calculate the loss from the fake images. That's this line, loss discriminator fake, using the same criterion, that is a loss function which will be BCE loss. To that I'm passing output and label, that is the predicted ones and the ground truth. And obviously after that again the backward propagation. And this line again, it is just for keeping a log of my my calculation so that I can print it while running the train method. So the total discriminator loss at last, because now my fake images and real images both have been run through the discriminator network. Now the total and the individual loss has already been calculated. So now the total loss will just be the addition of the real loss and the fake loss. And finally, optimizer D dot step. Optimizer D is the optimizer which we have to pass as an argument later. We will see in a second. And then the step function to update the weights, and move on for the next step, which is my generator network. This will be generator, update generator, GENERATOR. And here my generator training will start. And just exactly we did in the discriminator. First I'm bringing in 0 grad to set the gradient to 0 to offset the accumulation behavior that PyTorch otherwise will do. And then the label.fill and filling them with real labels. Real labels are all 1 values. So this is a single value, single scalar value of 1. We have to pass it as an argument. And why I'm doing this is because I'm setting image label vector values all equal to 1 to fool the discriminator network. Because in the next line here, I will be classifying the fake images with my discriminator network. So I'll be passing the discriminator network all the fake images, and I want discriminator network to think that they are real images. That is, I'm trying to fool them. And we'll see that how much of this effort of fooling, of trying to fool the discriminator actually work. So basically what's happening in this line is important to understand that the discriminator net, I am passing fake images, but all the labels of these fake images has been defined to be 1. That is, that's where the crux of the story in the generator, that is, generator is trying to fool the discriminator network. And then if it fails to do that, that is, if the discriminator really cannot think that is the fake images are real, that means the generator failed. That will be the value of the loss of the generator network, and that's what I'm doing in the next line here. That is, loss from the generator network is defined as the loss between this output and this label, and this output is coming by passing to the discriminator network all the fake images while the labels are all 1. That is, these images are all fake, so the label should have been 0. That is, they are fake labels, but I have passed all labels to be 1. And then that will become my loss from the generator, to the extent the generator fails to fool the discriminator. And after the generator loss, then I'm doing the back propagation with the backward method, and also creating this line is just for logging purpose. And finally, optimizer G.step, and this is optimizer for the generator network that I will pass as part of the arguments, and then the step method to update all the weights and move forward. Okay, and then these lines are just for logging during while all the epochs are running. So basically I am just outputting the epoch number, because epoch will start with 0, so I'm adding 1 to it. And total number of epochs, that is total number of so it will print something like which epoch I am currently out of my total number of epochs that need to run. And also it will print my num batches and loss during the epoch, that is both the discriminator loss and the generator loss, etc. Yeah, so that's my printing from the epoch. And then I am setting generator net dot eval to eval mode, because now I want to plot the images between the epochs. And because this plot images will plot the image that is a fake image that were generated by the generator network. And finally, before the final step of the train function, I have to set the generator net again to train, so that my gradient calculation, etc., is again turned on. So that's where my train method actually ends. So the entire train method goes on till here, and I trained both my discriminator and generator. And then the next and the final step in this entire project is to do this training. Before that, I have to initialize all these arguments variable that I have to pass to the train method. And that's what these few lines are all about. Here in these lines, I'm just creating all the arguments. Batch size, I'm keeping it at 256. Output path, because I was running this in Google Colab, so this is just the default session storage path in Google Colab. And so I'm pulling the MNIST dataset by invoking or executing this get data loader method that I have defined in my utils.py file. Device, I think I have already defined it at the very top, so I don't need it here. I can just delete it. Let's quickly see if I have defined it at the top. Yes, I have defined my device at the top, so I don't need it below again. And then these discriminator net and generator net is just the class implementation of discriminator and generator. And note these numbers, very important. Number of channels, I'm passing 1 to discriminator because it's MNIST dataset. So both the discriminator and generator will take this argument as 1, because output from the generator will need to be one number of channel, and for the discriminator as well. For both for the input to the discriminator also need to be, the number of channels need to be 1, because MNIST is one channel dataset. And number of discriminator filter and also the number of generator filter, both I'm defining to be 32. Remember when we did the this generator and the discriminator, we need that number generator filter to feed into my out channels for my generator class at the very first conf transpose 2D layer. Similarly, this number of channel will be included in all the conf 2D layer to determine my number of channels. So again, the generator network, the number of channels continues to decrease through the layers, and in the discriminator class, this number of channels continues to increase. The first conf 2D takes only the number of discriminator filtered. Then in the next conf 2D, I'm multiplying by 2. Then in the third conf 2D, I'm multiplying by 4. So in the discriminator, it increases. Anyway, so this num generator filter, I am defining to be 32 for both of them. And then I'm transferring both these tensors to my device. Very important. Otherwise, you will definitely get error. Criterion, as this is a binary classification problem, so I am using BCE loss. And optimizer D for both my discriminator and generator, I am creating the optimizer. I'm using the optimizer to be Adam optimizer. And learning rate, the very standard one, 0.001. And here, real label and fake label, I'm defining them to be 1 and 0 respectively. And because I need float number, and that's what I'm using it like this, that is 1.0 or 0.0. So initially, if you use it just like this, it will be taken as an integer and you will get an error. And that's when I initially had to use the torch.float tensor inside my network, inside my training code here that I deleted a while back. So yeah, this is minor point, of course, that you have to initialize your real labels and fake labels to be float value. And yeah, number of test samples 16. This is just for the plotting purpose. This will be fed into my this function when I am plotting. Yeah, plot images, that will take this number of test samples, because that many samples it will actually plot to give me and show me my result. And fixed noise, this is my this is the noise variable that I'm creating with torch.randn. Number of epochs, I was testing initially but 20, but I would suggest if you keep it at something like 50, you will see really good images. That is, the fake images produced by the generator will almost look like real MNIST images. And noise vector, obviously, as per the paper, it has to be a 100 element vector. That will be fed into the very first layer to the generator input. And finally, I'm executing the train method here with all these arguments that I defined here. So it takes quite a few arguments. All right, now all these files are completely ready. I will just fire up a Google Colab instance and upload these three files and run a Jupyter Notebook to see the actual result. Let's go back. Actually, keep my number of epochs to 270, because I think that's when you can really see almost real images from the generator network. And here I am in my Google Colab. I have just created a very simple Jupyter Notebook. It will only have kind of only 2 cells. That's all, because you will see that why you need just this 2 cell, because all my code is already done in this in the different 3 files that we have seen. Now here in the Google Colab, I will just upload those 3 files individually and run these Jupyter Notebooks to see the result. But first, let's see, my runtime is using the GPU. Yes, I'm using GPU. And let's check what kind of GPU I got by running these command NVIDIA-SMI. All right, I got a powerful GPU, Tesla P100 with 16 GB of memory. Okay, now yeah, clear this output. And the next line, I am firing up my Google Drive, because I have to my MNIST dataset is residing in my Google Drive, so you have to just write this to code to connect your Google Drive. Just run this cell and it will prompt you to connect the Google Drive here. And after running, it just will say that mounted at content/drive. And now you have to upload those 3 files that is in my local machine. So just upload those 3 files. I have DCGAN.py, train.py, utils.py. All right, they got uploaded. So you can just double click and check that this is my train file. Okay, looks awesome. This is my DCGAN file. And this is my utils file. I am zoomed in too much, so that's why it has taken the entire. Let's just bring in my Jupyter Notebook. Okay, so I have these 3 files uploaded, and remember, my train file has already imported all the modules from DCGAN and utils, the other 2 files. So my train file has everything it needs. So only thing I have to do for this project to run properly is run this command. That's pretty much it. That is Python train.py, and it will run it. Let's just run this cell. And we can see the epoch just started running. Yeah, so that's the kind of output you will see. Let's zoom out a little bit. Let's close this. Yeah. So at the end of the first epoch, I have my G loss is this, dx, this variable that I have defined at the very top. That's 1. Yeah, so okay, so here I'm running for 75 epochs. So obviously I am not going to wait. I will just show you the final result. And after running all the epochs up to 75, that is total 75 epochs, this is the final image that I got from my generator a class. That is, these are all fake MNIST images generated by my generator class, which started with only 100 vector of 100 elements, that is a noise vector, and created this image of MNIST after 75 epochs. So you can already see they are really looking almost like the real MNIST images. And just to test, I actually ran it up to 125 epochs, and after 125 I got almost in exactly the original like images from my generator network. So that was my DCGAN implementation with PyTorch for MNIST dataset. And obviously the GitHub link I will put in the description of the video. The GitHub repository has numbers associated with each video, so just search by the numbers. That pretty much wraps up this video, and all my upcoming videos will all be on some great computer vision projects and algorithm with PyTorch and TensorFlow. So stay tuned, and if you have not subscribed yet, do subscribe. And if you like this video, smash the like button. Thank you for watching.